three most common modes to perform infrared spectroscopy are Fourier transform, dispersive, and non-dispersive spectrophotometers. This video will discuss Fourier transform spectroscopy, also known as FTIR spectroscopy. More specifically, the theory, instrumental components, and advantages of FTIR spectroscopy and spectrometers will be examined. The first commercial infrared spectrometers were available during the 1950s. These IR spectrometers utilized prisms to disperse and select different wavelengths of IR radiation, but were largely limited to the narrow region between 4,000 to 700 wave numbers. Grading IR spectrophotometers were subsequently favored over the early prism monochrometers, but suffered from high cost and slow operation. Astronomers attempting to observe weak infrared signals from distant stars and planets in the far IR region of the spectrum, approximately 400 to 10 wave numbers, could not obtain clear or accurate spectra with the prism and grating spectrometers of the 1950s. This has then spurred the development for analytical techniques with high degrees of resolution and accuracy, from which FTIR spectroscopy was realized. It was not until the late 1960s that FTIR spectroscopy was made practical for regular laboratory uses. Frequency domain spectroscopy relates the incident frequency or inverse wavelength of radiation to the power output. Conversely, time domain spectroscopy, which FTIR spectroscopy operates upon, measures the radiant power as a function of time. For the purposes of this video, only two monochromatic wavelengths of light, oscillating with frequencies nu1 and nu2, will be discussed. When plotted in the frequency domain, meaning that frequency is the x-axis and power is the y-axis, nu1 and nu2 display a characteristic peak at their respective frequencies. When each wave is plotted on the same time domain spectrum, meaning that time is the x-axis and power is the y-axis, one notices that in some areas of the spectrum the two waves are slightly offset or constructively interfere. When the difference between nu1 and nu2 are plotted on the time domain, the effects of the constructive and destructive interactions due to the in and out of phase waves becomes more obvious. As time increases, the offsets between waves of varying wavelengths will become greater, and the wavelengths will become more out of phase, leading to destructive interference. Consequently, as time increases, the intensity of the power decreases. Nevertheless, a time domain spectrum and a frequency domain spectrum can provide the same exact information. The entire time domain spectrum can be displayed all at once, thereby significantly decreasing the amount of time required to perform frequency domain scans. Thus, converting from the time domain to the frequency domain can result in highly precise and quick analyses, while still obtaining the necessary spectroscopic information from the frequency domain. This can be accomplished using a Fourier series, where a curve is decomposed into the sum of sine and cosine terms. There are five main components of an FTIR spectrophotometer. 1. A source of infrared radiation. 2. A Michelson interferometer and beam splitter. 3. The sample. 4. A radiation transducer. And 5. A signal processor. The Michelson interferometer will be discussed in depth due to its significance to FTIR spectrometers, while the rest of the components, although still important, will only be mentioned briefly. For most FTIR measurements, a continuum source, mostly acting as a blackbody radiator, is utilized as the generator of IR radiation. For near IR measurements, typically between 10,000 and 4,000 wave numbers, a tungsten halogen lamp may be used. The mid-IR region, which is between 5,000 to 400 wave numbers, will most likely require the use of a heated silicon carbide glow bar. For most IR measurements, a mercury or noble gas discharge lamp can be used. One practical and very useful attribute to conventional IR spectroscopy is that solid, liquid, and gas samples can be analyzed. This is also true of FTIR spectroscopy. Each phase will have to be held in a different sample holder, but all phases can be analyzed, given the proper sample preparation procedure was followed. Each characteristic region of the IR will generally require a separate detector to be fitted on the FTIR spectrophotometer. For near IR measurements, which do not require sensitive equipment, an indium galanite arsenide photodiode array will be utilized. For mid-IR measurements, either a deuterated triglycerin sulfate or lithium tantalate detector can be used. Each relates intensity of the IR signal to the changes in temperature as the light strikes the detector surface. Finally, for sensitive far IR measurements, A mercury telluride, cadmium telluride semiconducting alloy cooled in liquid nitrogen is utilized to measure the temperature-dependent electrical resistance as IR radiation hits the detector. The signal processor plays an important role for FTIR spectroscopy in that it performs a Fourier transform conversion from the time domain to the frequency domain, a process that would be extremely difficult and time-consuming if done by hand. Like many other analytical instruments, the signal processor is the computer. The Michelson interferometer is an instrumental component of the FTIR spectrometer that is integral to the distortionless conversion of the time signal to the frequency signal without losing any of the information from the time signal. The interferometer is comprised of an incident light source, a collimating lens, a beam splitter, a stationary mirror, a movable mirror, and a detector. An incident beam of light is collimated by the collimating lens and will be split into two beams of equal power by the beam splitter. One half of the radiation is reflected and is subsequently reflected from the stationary mirror, while the other half is transmitted and then reflected by the moving mirror. The two beams will then hit the beam splitter again, where two halves recombine and strike the detector. The other two halves are transmitted to the source and are not used for any measurement purposes. The intensity of light that reflects off the movable mirror will vary depending on the position of the mirror when the radiation strikes it. Thus the detector will measure the variation in intensity between the two recombined beams as a function of their different path lengths. The difference in these path lengths is termed the retardation, which is represented by the variable delta. The plot of the radiant power in the time domain versus the retardation, delta, is an FTIR interferogram, which is described by a cosine function. The cosine function reaches its maximum and minimum when the movable mirror is situated at a distance of 1/2 the wavelength of the radiation. The time t it takes for the mirror to move that distance at constant velocity v, where v is equal to delta over 2t, can be summarized by the following equation: v times t equals lambda over 2. The frequency of this signal is simply equal to 1 over t, which when solving the above equation for t and plugging it in, results in the equation f equals 2v over lambda. This equation can further be simplified by rewriting the previous equation as f equals 2v times nu, where nu is in wave numbers. As one can see, the frequency of the interferogram is proportional to the frequency of radiation. The final equation for frequency is important for the conversion of the time domain to the frequency domain. The cosine function of the interferogram can be expressed as p of delta equals b of nu times cosine of 2 pi ft, where b of nu is a constant that accounts for the intensity of the light source. Substituting the frequency variable for its equation, the resulting equation becomes p of delta equals b of nu times cosine of 4 pi times velocity times nu times t. Using the relation for the velocity derived previously, the equation for the cosine wave then becomes p of delta equals b of nu times cosine of 2 pi delta times nu. The sum of all the cosine functions that comprise the interferogram can be expressed as p of delta equals the integral from negative infinity to infinity of b of nu times cosine of 2 pi delta nu with respect to nu. The above equation can be rearranged to solve for the Fourier transform, whereby some interferogram in the time domain is converted to some intensity in the frequency domain. The resulting equation, b of nu, equals the integral from negative infinity to infinity of p of delta times cosine of 2 pi delta nu with respect to delta. FTIR spectrometers offer a number of advantages over conventional dispersive and non-dispersive instruments. The first is the enhanced resolution associated with FTIR spectroscopy. The resolution of the spectra scales to the reciprocal of the retardation. Thus it is possible to obtain the high degrees of resolution simply by moving the mirror. Two other major advantages of utilizing FTIR spectroscopy include the improved signal-to-noise ratios and high optical throughputs, both of which are useful for detecting samples with either high absorbance or weak signals. Other advantages include very fast scan times, the lack of a requirement for external calibration, and the fact that the technique is non-destructive. The only significant disadvantage of FTIR spectroscopy is that the instrumentation is more expensive than dispersive IR spectrophotometers.